track of my dissertation, looking at trait-dependent extinction in this group of marine invertebrates called brachiopods. I'm looking at this in kind of a larger context where I'm taking a lot of ecological data and using that to try and predict taxon duration. So just to start, these are all like species or even higher level traits. And so there's a little bit of theory as to why we would think about selection on traits and aspects like that. So basically, if a species has a trait that's good, or defined in whatever way you want to mean, it's beneficial for existence, they'll probably persist longer than species lacking that trait. This is rather basic. So this is actually consistent with some theory talking about what is a more inclusive statement of fitness, which is Cooper defined as kind of the expected time or expected duration of a taxon is some measure of fitness. So if you have differences in durations, you have differences in fitness because selection, adds up. So when looking at trait-dependent extinction, why would we even look at extinction in the first place? Well, kind of, when we have macroevolution, there are two things that kind of fade, shape diversity. You have speciation, you have extinction, and extinction is second only to speciation. So there are two major approaches for looking at kind of trait-dependent extinction. Phylogenetic comparative, if you've heard of the whole diversity suite or other things, it's the same concept. Or paleobiological, which has another long history. So the problem with looking at trait-dependent extinction, or even just extinction in general from a phylogenetic comparative perspective, is if you have trees of only extant taxa, it's hard to think about extinction because nothing's called extinct. You've just not sampled it. So instead, I'm looking at the fossil record, which is itself an imperfect observation of extinction, but at least has observations of extinction and taxon duration. That's the wrong direction. So we'll start with a basic observation from the higher paleobiological literature on levels of selection. That at the Cretaceous Tertiary mass extinction event, biological traits, except geographic range, so things like larval condition or infaunal versus epifaunal, seem to have no effect in the case of bivalves on taxonomic survival at that one boundary. So this gives up a kind of basic question. How does the effect of emergent traits, or even aggregate traits such as species traits, affect duration, which I'm calling extinction selectivity, because it's the selection with respect to traits? And then how does that vary with expected duration, which I'm calling extinction intensity? For example, with a lot of taxa, or if taxa originating at the same time, if many of them are going to go extinct very quickly, we would say that's a high intensity period. But if many of them are going to go extinct very late, we would say that it's a low extinction intensity time. So my approach is just a hierarchical Bayesian survival model where we have all of our effects varying by cohorts, and then we are estimating itself the correlation between the change in the effect of traits between cohorts. So just to kind of put that intensity selectivity thing in a kind of graphical framework, we can think of, at one point we have the effect of a trait, which could be negative or positive or non-existent on duration. And then we want to see, well, how does that vary when we look at different periods of intensity? Low intensity versus high intensity, does it change? Does it change sign? Does it just increase or decrease in magnitude? So I look at brachiopods, which are an uninteresting group of marine invertebrates that have, these are specifically articulate brachiopods, which have no economic importance, as opposed to the inarticulate brachiopods, but they don't have anything interesting to say. So we look at these because they have probably the most complete fossil record imaginable. And I'm looking at specifically the post-Cambrian Paleozoic. So to put that in context, I'm looking between the time range of 488 million years ago to 252 million years ago, so it's about 200 million years of evolution. We're measuring duration just as very coarse at the number of stages a genus exists through, where, just so you know, stages are not really just 1 million year things. They're awkward and not uniform in their duration. So we have to use a rougher estimate there. Looking at a bunch of traits, where all these effects are varying, we're looking at geographic range because that's super important, body size because everyone asks you to, and environmental preference with respect to the taxon's preference for being on an epicontinental sea or on an open-facing ocean. So epicontinental seas don't really exist anymore. These are periods where we have higher sea level and the ocean comes on top of the continent, on top of the craton, and you can have taxa living in the middle of the continent as opposed to on the edge, just on the edge for these marine groups. Also looking at sampling using some well-known measure of the gap statistic, which is this idea of how much is missing in its record, how solid through its range we see it. This is hard to calculate for some really short duration taxa, so I use some cool Bayesian framework to impute that data and make it up as we go along. So the basic idea is we get a hypothesis of geographic range. We have two species, one is large, one is small. If you destroy half the world, the one in the small range does really badly versus the one in the large range. I mean, yeah, I could have drawn the yellow circle up high, but you get the idea. So with respect to environmental preference, we can just go back for a hypothesis or how to essentially develop our priors. Go back to Simpson in the 40s, where he's talking about this concept of the rule of survival of the unspecialized. It's a rule in the sense that it's not a law, because it's common but not universal. And the basic idea is that if you're a generalist or in the middle of a gradient, you're probably better off than if you love the edges, because if you love the edges, if those environments disappear, you have nothing to go to. So just to give a graphical depiction of the model, our main piece of interest is this idea of expected taxon duration for some origination cohort, where we take into account varying biological traits, where we allow, for example, environmental preference to have a nonlinear relationship with duration, body size, geographic range, measuring them correlations. We're also allowing for age-dependent extinction, because that's a thing, and putting in that sampling metric, just to kind of help understand the relative magnitudes of the effects. So this is a fun little diagram. It takes a while to take apart, but the whole idea is here are the estimates of these effects as varying through time. So here's intensity, where low values indicate periods of low intensity and high values are high intensity extinction. And then for these trait effects, low values indicate good for duration, high values bad for duration, except in the case of the curvature environment, which I'll get to in a second. But we can see that there's a lot of variation in intensity. Geographic range has some mediocre variations, rather tight relative to overall mean. You see environmental preference has quite a bit of variance. Environmental curvature has some other variance, and size has virtually no effect. This weird spike area in the middle, you might see, that's the Frasnian-Fabanian boundary. It's a huge extinction event. So that'll come out interestingly. We can look at the overall relationship between environmental preference and some transformative duration, where if here is the average preference going through here, we would say that one, yeah, super nonlinear, where n members do way worse than things in the middle, and then a slight, if not particularly strong, favoring of taxa that favor epicontinental seas or not. This makes sense. Brachiopods are sessile filter feeders and are well known to be loving of epicontinental sea environments. Probably why there are not a lot of them now. So just to give you 4 examples before I show all 33, here's the variation in the environmental effect between a few cohorts from the Encian to the Fransian, where we can see black being the overall relationship from the previous slide, and the blue being 100 draws from posterior. We can see that, yeah, there's quite a bit of variation. Sometimes it's very strongly through this single mean, where we have bad things with the n members, or everything's terrible except in the middle. We get shifts, or we get things that just look like the overall. And that might be because of smoothing due to low data, but it's still, we're getting the same concepts. So we can take that to the whole range, and you see, yeah, those 4 stages, which are here through here, represent kind of the general trends, where we see shifts or leans, or things going very flat when there's not a lot of difference. But we can see quite a bit of variation. In fact, periods where we have very low extinction intensity are rather flat versus high extinction intensity, where we increase this curvature. So we can look at that as our estimated correlation matrix, where the upper triangle is median estimates for the posterior, and the lower triangle are idealized correlation. Circles, no correlation, cigars, correlation. And the only ones that have at least 85% posterior probability of being their sign are the relationship between intensity, or this B-intercept, and the effective geographic range and environmental preference. This is that where the peak in the environmental preference curve is. So the way to interpret this is essentially that as intensity increases, the importance or magnitude of the effective geographic range increases. And that as intensity increases, the importance or magnitude of preferring epicontinental environments increases as well. This is consistent with work by Michael Foote and Arnie Miller looking at cross mass extinctions through the Paleozoic and Mesozoic, differences between different environments. During mass extinctions, epicontinental taxa tend to do a little bit better. So just to give a basic effects summary, geographic ranges, I didn't really talk about it, but it's consistent with prior expectations and has low variance. The whole idea that if you have a bigger geographic range, you have a longer duration, we know that because it's the largest effect, and we've known it forever. There is virtually no effective body size with very low variance. Within that, there might be a stage or two where it actually does matter. Epicontinental environment preferences are slightly favored, but this has very high variance, as we can see. Just to go back, very high variance, where it's going all over the map, but in general, it's over to one side. And then finally, that concave down curvature, super strong, medium variance, but there is approximately a point, like a 1% probability of having a concave up, so a reverse relationship where specialists are favored. So I would say that probably is never happening. So we can start to kind of give this a macroevolutionary process where we say, these are two statements that say approximately the same thing. The magnitude of the effective geographic range and environmental preference increases in extinction intensity. So what does this mean? It means that as extinction risk decreases in this case, the differences between taxa matter less. Everything's just living long. But you would say that if the extinction risk increases, the differences between taxa we would expect matter a lot more. So I'd like to thank a bunch of people. They gave me money, they told me to write in English, and Arnie Miller gave me all the epicontinental versus open ocean assignments. Just to give context, this is over 50,000 occurrences across 2,000 genera. So he went through my hand and did it. I really appreciate it. So I have time for questions. Thanks.
Particularly in an entanglement where taxa that have large ranges tend to have nil or low environmental preference because they're more likely to show up in multiple types of environments?
There is a possible interaction. Something I would consider alternatively would be taxa that have these more intermediate environmental preferences are longer lived, but the question is, are they flexible naturally? Are they just true generalists, or are they adaptive? Or are they adapting with the environment and are just flexible specialists? So because we are averaging over their entire duration.
Yeah.
So that's a different analysis where you would look at change in environmental preference over time. Yes?
Are there any groups of organisms where you would expect to see a different result other than brachiopods?
What do you mean?
Like a different relationship. So are there any, it just seems like brachiopods are a very specific organism, right? So for instance, you said that they kind of preferred those, I forgot what you called it.
Epicontinental.
Epicontinental.
On top of the continent.
And that's actually time, so.
Sorry. But if anyone wants to talk to me,